So hello, and welcome to the second of the Phys 121 lectures. This lecture is going to be about vectors. Okay, and so I just want to sort of stress a couple of points before we get going. One is vectors are super important. Okay, like in a subject like kinematics or dynamics, you have position vector, velocity vector, acceleration vector, force vector, angular momentum vector. So everything is vectors. And so and everything, really happens in 2 and 3-dimensional space. And so you really need to start to think in terms of vectors. It's a super important basic skill that physicists need to have. So I want to encourage you to really work on your familiarity with vectors, how they work, the notation, all that stuff, so that you're really comfortable with vectors. Because by the time you get to second year, it's assumed that you're super comfortable with vectors, and you can just do, vector calculus. You start doing vector calculus and stuff like that. So I really encourage you in this, first introductory course to physics to make sure that you master vectors. The second thing I need to say is that I'm going to assume that you've seen vectors either in high school or like a high school physics course or a high school math course. And so I'm not going to start at zero. If you need to start at zero, there's a really nice discussion about vectors in the textbook. So I encourage you to do that. Really, all I'm going to do is assume that you know the basics about vectors, and I'm going to just show you how vectors are used and the notation that physicists use when they're using vectors to describe and work through simple problems. Okay, so I also, appreciate that some of you may have seen vectors before in a different notation. So I really encourage you to adopt the notation that we, be flexible in your thinking and adopt different and be able to work within different sorts of notations for vectors. It helps with your flexibility of thinking and all that kind of stuff. And at the end of the day, you want to be able to speak the same language that physicists speak. And this particular kind of vector notation I'll be showing you is pretty standard amongst physicists. Okay, so the first thing we want to do is we're going to imagine, like in kinematics and dynamics, we have objects that are moving through, in general, 3-dimensional space. And so we're going to assume we're in an inertial reference frame, and so we need to establish a coordinate system so that we can describe positions and velocities and all of that good stuff. Okay, so the first thing we do is we choose an x, y, z coordinate system. Okay, and whenever you choose a coordinate system, there are 2 important choices that you need to make. So one of them is the origin, so where x, y, and z are 0, and the other is the orientation of the coordinate system. So for lots of simple problems, it doesn't matter so much. But as we get more into more and more advanced problems, especially to do with angular momentum and so on, this becomes much more important. So, for instance, a typical simple problem is we have an inclined plane here, and we have a mass which is going to let go, and it's going to slide down the inclined plane. So its motion will be in that direction. So the origin. An obvious place for the origin is the object is starting there, its center of mass is there, and so let's choose that as the origin point O, and then we're going to release it and it's going to move. And then the second choice you need to make is the orientation. Do you want the x-axis and y-axis to be horizontal and vertical, or do you want that pair of axes to be tilted? So in this case, it's pretty clear that you want the coordinate axes to be tilted. You'll choose, say, the x-axis to be parallel to the incline, down the incline, so that when you release the mass, it moves only in the x direction, and there's no motion in the y direction. If you chose your coordinate orientation to be like this, then there would be motion both in the x-axis, along the x-axis, and the y-axis, and that would unnecessarily complicate it. Okay, so whenever you're choosing an XYZ coordinate system, think a little bit about the origin and think about the orientation. Those choices are arbitrary. Whatever choice you make is going to work. Okay, so let's just start with kind of a random example. Let's just put a coordinate system here. Let's just choose the origin, say, at this point. I'm just going to look at my notation because this is a complicated diagram. I don't want to get it too messy. Okay, and so we'll choose this origin point over here, and we're going to imagine that we've got some object like a baseball. We throw it and it moves on a parabolic free fall trajectory like this through, say, two-dimensional space. And so we'll choose the x-axis to be horizontal and to the right, and we'll choose the y-axis to be vertical and up. And so that's our choice of origin and our choice of orientation. Great. And now we're able to describe the motion of any object in this two-dimensional xy plane. We could also add a third direction, the z direction, which comes out of the page. And typically the z direction is chosen in a right-handed sense, a right-handed coordinate system. So what that means is you take your right hand, and which might look like my left hand, because this is a mirror reversed video. But anyways, so you put your right hand in the direction of the x-axis, and you let your fingers curl in the direction of the y-axis, and then the z-axis is coming out of the page at you. Okay? Great. So that's a right-handed XYZ coordinate system. And then what comes with that naturally are three very important vectors that are called I hat, j hat, and k hat. So I hat lies along the x-axis and is of length 1. And I'm just going to make sure this diagram doesn't get too messy. I hat, j hat, and k hat. Okay, so let me just sort of define these. So I hat, j hat, and k hat. There are two very important properties of these vectors. One is they are dimensionless. Okay, so they don't have any dimensions, like they're not a length, they're not a mass, they're not a velocity, length over time, they have no dimensions. Okay, so they're dimensionless, and they are also unit vectors. Okay, so the length of this vector, and this vector is just the numerical value 1. So I hat is a vector pointing in the direction of increasing x and has length 1. J hat is a vector pointing in the direction of increasing y and has length 1, and similarly for k hat. So they're unit vectors, length 1, and they're dimensionless. Okay? The dimensions from vectors come from what you multiply these guys by. Okay? So the important thing about these basis vectors, these unit dimensionless vectors, is that you can express any vector as a linear combination of I hat, j hat, and k hat. So a little bit of I hat plus a little bit of j hat plus a little bit of k hat will give you any vector in three-dimensional space. So that's the idea. So for instance, let us suppose that we have a baseball here and we throw it like this. So the initial position of the baseball is, say, let's say over here. Let me just think for 1 second. There, 3. Yeah, so let's put it approximately here. Okay, so let's suppose that that's the initial position of the baseball that we are throwing. And so there will be, so the initial position vector is a vector that points from your coordinate origin to the initial position. So it's a vector of this length and exactly in that direction. Now we're going to imagine that this motion is happening in this two-dimensional xy plane, and so z is equal to 0 for all of its motion. So this is the initial position vector, and we'll call that r0. So in physics, position vectors are almost always denoted by the letter r with a vector sticking on top. The subscript 0 indicates that, oh, it's the initial position. It could be r0 or r subscript I for initial position. Okay, so we'll say r0. This is equal to the initial position vector. Okay, and so so let's see. So let's give it some values here. So in general, an initial position vector would be some linear combination of I hat, j hat, and k hat. Since we're restricting our motion to the x and y directions, it'll just be a linear combination of I hat and j hat. So we would write it as x0 I hat plus y0 j hat. Okay? And so if we look on this diagram over here, so x0 is how much we need to move in the I hat direction to get to the horizontal position. Well, we need to go this amount over. So this is x0 is this length over here. And in this case, it's negative. x0 in this particular example is a negative number, like negative 3 meters, for instance. Okay, and y0 is how far we need to go along the j-hat direction to get to that point. Well, that's this distance along that triangle. So this is y0, and in this case, y0 is positive. Okay, so that's how you would write a general position vector in two-dimensional space. And let's give it some numerical value, for instance. So this is, say, negative 3 and positive 4. So we would write this as negative 3 in the I-hat direction, positive 4 in the j-hat direction, meters. Okay, so this is the standard way that you will write vectors in this course. So it'll be a linear combination. There'll be numbers in front of I-hat and j-hat, all in brackets, and then on the outside of it, you tack on the units. So if it's a position vector, you'll have meters sitting there. If it's a velocity vector, you'll have meters per second sitting there. If it's an acceleration vector, you'll have meters per second squared, and so on. Okay, so it's really just, dimensionless numbers times I-hat and j-hat, and then the dimensions or the units sit at the very end like that. So the dimensions, so remember that if we have an object and we want to ask what are the dimensions of it, well, we put square brackets around it. So the dimensions of this initial position vector are length. Okay, it's the same as the dimension of the I-hat and j-hat components. So x0, that number has the dimensions of length, and units in SI units, meters. And so these are all of the same dimension, length. Okay, very good. Okay, so now we can think a little bit, say, about, so we do have limited space on this board. So I'm just going to draw a little dividing line over here, and we're going to go up here. Okay, and so the magnitude of a vector, so the magnitude of the vector r0, of that position vector, so what you do is you take the vector r0, that's r0 with a little vector sign on top of it, and you put parallel bars around it. That indicates the magnitude or the length of that vector. Okay, and very often physicists will not use such complicated notation, and they will simply go r0. So r0 without the vector on top, that means the length or the magnitude of the vector. And so you can see just from Pythagoras' theorem, we have a little triangle here, the length of the hypotenuse of that triangle is the magnitude of r0. Well, that's just that squared plus that squared square root. And so it's the square root of x0 squared plus y0 squared. And so you can see that that's always a positive number, or 0. And in this particular case, if we, well, let's actually just work it out. So in this particular case, the initial position vector is negative 3 meters in the x direction and positive 4 meters in the y direction. And so when we work out the magnitude, we will have a negative 3 meters for x naught squared plus positive 4 meters squared. And then take the square root. So you have meters squared under the square root, and so it becomes meters, and it's 3 squared plus 4 squared is 9 plus 16 is 25 squared, and that is 5. So it's 5 meters. So the distance from the origin to the initial position of our baseball or whatever it is 5 meters. Okay, very good. What else should we say? Oh, the direction. We should talk a little bit about the direction. So the magnitude, and now the direction. Okay, and so the direction of the vector. So typically, now of course in three-dimensional space, the direction requires two angles, just the angles on a sphere. If you're in three-dimensional space, if you have motion just in two-dimensional space, then the direction of a vector can be specified by a single angle. And usually, conventionally, what you do is you take the angle going counterclockwise from the positive x-axis. Okay, so here's the positive x-axis. So in which direction does the initial position vector r0 point? Well, you go counterclockwise, and so it sweeps through this whole angle here. And so there's some angle here. And we'll call that, what are we going to call that? Phi 0, for instance. Okay, so we can work out the tangent of phi 0. So tan of phi 0 is basically the slope. And so tan is rise over run. So slope is rise over run. Okay, so when we look at this, we ask ourselves, you know, how far do we need to rise up to get to this point? Well, that's y0. How far do we need to run? Well, it's x0. In this case, we're running in the negative x direction. So rise over run is just, how should we do this? y0 divided by x0. Okay? And so then you have the tangent of the angle phi 0 is y0 over x0. And so then you just work out what phi 0 is by taking the arctan of y0 divided by x0. Okay, and so let's actually work that out. So we get arctan. In this case, y0 is positive 4 meters. And x0 is negative 3 meters. And you'll notice something important, that the dimensions, the meters cancel out. So whenever you're dealing, all angles are dimensionless. Okay? Whenever you have to take a function of some variable, that variable has to be dimensionless. Okay, so arctan, so angles are dimensionless. Okay, and so you see the meters cancels out. So it's arctan of a dimensionless number, 4 divided by negative 3. And so when you plug that into your calculator, so what do I get when I plug it in my calculator? I get negative 53 degrees. Okay, you should also be familiar with irradians. Okay, we'll just use degrees in these examples. Okay, so great. So we look at this and we say negative 53 degrees. Well, let's see. So in the counterclockwise direction, we go negative 53 degrees. Oh, wait a minute, that seems wrong right away, because negative 53 degrees is about down here. And so it's telling us that the direction of this vector is not that, but exactly 100 degrees opposed to that. And so why did that happen? So why did we get the wrong answer? We got the wrong answer because your calculator can't tell the difference between negative 4 divided by positive 3 and positive 4 divided by negative 3. Okay, so you have to be careful about this. Can't count the number of times I've seen this mistake. You guys make this mistake on tests and stuff like that. Okay, so you have to be sort of in communication with the problem, thinking about it. Okay, so negative 53 is obviously the wrong answer. Okay, and so so really you need to add 180 degrees to that. So you add 180 degrees, so plus 180 degrees. And so the real answer is, what is the real answer? 127 degrees, positive 127 degrees. So be careful about that little problem with calculators. Okay, so it's really positive. This is 90, this is 0, this is 90, this is 127. So that's right. Always be sort of checking your math against your diagrams to make sure that things are sort of, you know, making sense and working together. Okay, so very good. So then what we're going to do is we're going to give this baseball some initial velocity. And it could be anything. I'm just going to pick an arbitrary initial velocity. In fact, I'm going to pick an initial velocity that is perpendicular to the initial position vector, you know, just for fun. It could have been in any direction. Okay, so we're going to launch it with some initial velocity vector, v0. And so then it's going to take off and it's going to go on some trajectory like this. Okay, through that two-dimensional space. So let's take v0. I wonder if I can fit this up here. I can fit it over here. So v0, okay, that's going to be your initial velocity vector. Initial velocity vector, we'll call it vector. Okay, great. And and so we'll give it some, we can write, remember that we can write any vector, including this velocity vector, as a linear combination of the I hat, j hat, and k hat unit vectors. Of course, this vector has only components in the I hat and j hat direction, so we should be able to write it as some number v0x in the I hat direction plus v0y in the j hat direction. Okay, very good. Yeah, and so let's actually give this some particular numerical value, and just to make things easy, all of the answers work out easily. We will take this v0 in order to be perpendicular to this vector. You might sort of know dot product already, and so you should have positive 4 here and positive 3 in the j hat direction. So let's take it as being 4 I hat plus 3 j hat. Okay, so for I hat, so it's more in the I hat direction than in the j hat direction. So it's a little bit tilted, a little bit past 45 degrees here, a little bit lower than 45 degrees. So we'll take that as our velocity vector, meters per second. Remember, all vectors in this course are written as dimensionless numbers, dimensionless number combinations of I hat, j hat, and k hat, and then you put the units depending on what kind of a vector is. If it's a velocity, it's meters per second. If it's an acceleration, it's meters per second squared, and so on. The units go outside of the brackets. Okay, so that's the proper way to write that, like a velocity. And then let's think about dimensions. So if we take the velocity vector v0, that is a velocity. It will have dimensions of length over time. And that's the same as the dimensions of the x component of the velocity, and it's the same as the dimensions of the y component of the velocity. They all have dimensions length over time. And so they have units of meters per second. So remember that when you're writing vectors as linear combination of I hat, j hat, and k hat, the I hat, j hat, k hat are dimensionless. The dimension of the vector comes from the coefficients in front of I hat, j hat, and k hat. Okay, so we have that. And so, so then the initial speed okay, so you remember that speed is the length of the velocity vector. Speed is either speed is always positive or 0. So initial speed, that's the magnitude. The magnitude or the length of v0, and so that's always going to be positive or 0. Speeds are always positive numbers or 0, and so that will be denoted by v0. So we can do this two ways. We can write it either as the vector v0, okay, and then put absolute value bars around it, magnitude bars around it, or we can much more commonly just write v0 without the vector symbol on top. That always means in this course the magnitude of the vector. And you know, you can play the same sort of game. You can take the x component, the v0x, and the v0y, and you have a triangle here, and so the length of that vector is given just by Pythagoras' theorem. And so this is the square root of v0x squared plus v0y squared, square root. So we have a 4 squared plus a 3 squared, square root is 25, and you're going to get meters per second. So this is 25 meters per second is the, oh sorry, 5. Square root of 25 is 5. Very good. Okay. And we can figure out the initial direction of motion, the initial direction. Okay, so let's give that a different angle. What did I call it here? Theta 0. Okay, so this angle here is theta 0. Remember that we always measure angles just conventionally in just a two-dimensional situation. When we measure angles always counterclockwise from the positive x-axis. So that's the positive x-axis. Counterclockwise is this angle of the triangle. And so the tangent of theta 0 is opposite over adjacent, and so it's vy0 over v0y over v0x. Okay, so the initial direction, theta 0. Okay, so that's going to be arctan of vy0, the rise divided by the run, v0x. Okay, and so we plug this in. We have v0y and v0x somewhere over here. Here. Okay, so we plug it in, and what we get is positive 37 degrees. And then you always have to ask yourself, is that the right answer? Or is it out by 180 degrees? Well, this is obviously about positive 37 degrees. So you're not wrong by a whole 180 degrees. Okay, so that's right. Just double check stuff like that. Be careful with your work. Okay, and so then finally, in general, so this is the initial position of the object. This is the initial velocity of the object. But now as time goes on, say at a later time, this is say at a time t, the position of the baseball will be here. And so we are trying to understand the position, describe the position of the object relative to the coordinate origin. So relative to the point O, how do we have to move to get to the position at time t? Well, it's this vector. Okay, so this is the position vector at some arbitrary time t. And as time t goes on, that position vector changes. Okay, and the velocity, and this is super important, whenever you're drawing trajectories of objects in 2- or 3-dimensional space, it is always true that the velocity vector is tangent to the trajectory. Because you know that at the next instant, at this instant of time t, the baseball is here. At the next instant of time, it will be a little bit further along the path. And so the velocity is the change in the position, the rate of change of the position vector. So if you go from this vector to this vector, the change in the vector is this one. Okay, so velocities are always tangential to the trajectory at any instant of time. So it's always easy to draw velocity vectors given a trajectory. So this is the velocity of the baseball at that same time t will be, say, this vector over here, tangential, of some length. Well, we figured out its length, it's 5 meters per second. Oh, sorry, over here it's 5 meters per second. Over here it's something else, okay? Very good, and so in general, the notation looks something like this. So we would say, we have, the position, and r with a vector on top is the position vector of an object, and in general it can be a function of time, and you can always write that as a linear combination of I hat and j hat and k hat unit vectors. So it'll be some x function of t, that's its horizontal position, or its position along the x-axis as a function of time in the I hat direction, plus y of t, some function y of t, which in this case at first increases and then decreases as time goes on. It first goes up, then it comes down. Okay, so that's in the j hat direction. And then if it's in 3-dimensional space, we would also add to this a z of t in the k hat direction. Oftentimes we just work in 2 dimensions. Okay, and the velocity vector at any instant of time can likewise be written as a linear combination of I hat and j hat. So instead of just, say, v0 in the I hat, and v0x in the I hat, and v0y in the j hat, it's just some function. So we'll call this, vx of t in the I hat direction, plus vy of t in the j hat direction. So x and y are functions of time, and they are components of the position vector. Vx and Vy are functions of time, and they are the components, the x and y, or the I hat and j hat components of the velocity vector v of t. And this vector is always tangent to the trajectory. Tangent to trajectory. Hopefully that didn't go off the corner of the screen there. Okay, so very good. So, so now we'll do an example. Let me just erase the board, and we'll do an example. Okay, so we were just talking about the vector notation, initial position, initial velocity, that sort of stuff, associated with a really simple example of, say, a baseball starting, over here at position vector r0 with some initial velocity v0 and would move along some trajectory. So we introduced the kind of notation associated with initial position, initial velocity, that sort of thing. Now what I'd like to do is I'd like to analyze that example, the kinematics of that example in pure vector notation. Okay, so really treating vectors as vectors, not splitting them into x and y components and so on, to really try to give you a geometrical feel for what vectors are and how they work. So I'm really trying to encourage you to get a deeper understanding of vectors through this example. Okay, so we're going to consider the previous example, except we're going to turn off gravity. Okay, so instead of, we're still going to start at this position, and we're going to still start with that initial velocity, but we're going to turn off gravity. Okay, and if we turn off gravity, then there's no force and there's no acceleration, so the velocity doesn't change, and so the baseball will just move upwards like this on a straight line with constant velocity. I take a baseball and I throw it like this. If there's no gravity, it'll just keep going on a straight line with constant velocity. So that's the first that's the first way we're going to look at this problem, the first example. So we're going to say initially, let's turn off gravity. And think about this tossing the baseball. So when we say no gravity, what we mean then is, of course, the force is going to be 0, which tells you that the acceleration is equal to 0, okay, which tells you that the velocity vector is constant. So it's constant and it's just equal to its initial value v0. Okay, very good. And so we know that kinematically what this looks like is the position vector as a function of time is just going to be the initial position, r0, plus v0 times the time. And we'll suppose that we threw the baseball at t is equal to 0. Okay, so when t is equal to 0 in this equation, the position vector is just r0. Now you might recognize this kinematical equation in x and y form. So this would be, x final is equal to x initial plus v initial times t. Y final is equal to y initial plus vy initial times t. This is the vector form of that equation. Okay, so it takes into account motion in 2 dimensions automatically just by using vectors. Okay, so the example that we were thinking about is here was our coordinate origin, O here, and we said that the initial position of the baseball was, say, over here. Okay, and so the position vector is a vector that points from the origin to the initial position. Okay, and we called that vector r0. Okay, and so in this kinematical formula, when t is equal to 0, then the position vector is just r0. Okay, when t is equal to 1 second, then we're saying that the position of the particle at t equals 1 second is the vector r0 plus the vector v0 times t. So v0 is a velocity, meters per second, times 1 second is meters. So v0 times 1 second is the distance, is the displacement, the vector displacement of the baseball in 1 second. Okay, so let's suppose it's a vector that's of this length. So this is v0 times 1 second. So that's the displacement, the change in position of the baseball in 1 second. Okay, so it looks like that. That's what that is. Okay, and then we say, well, what is the position at t is equal to 2 seconds? Well, the position vector at time t equals to 2 seconds is the initial position vector r0, which is located initially there, plus v0 times 2 seconds. Okay, so the displacement that an object, that this baseball will undergo in 2 seconds is the vector v0 times 2 seconds. Okay, and so it will double. Every second it will be displaced exactly this amount in that direction. So after 2 seconds, the position is there, and so on. So let's just sort of write this out. So this is the position. This diagram is going to get messy. So this is the position at 1 second. Then this is the position at 2 seconds, and this is the position at 3 seconds, at 4 seconds, at 5 seconds, and so on. So this is the position at t is equal to 5 seconds. Okay, so we have that. And so we can do this, we can look at this kinematical equation in 2 ways. We can look at it graphically. So that's the way we've been doing it so far. Okay, so the graphical analysis will say, well, the position at any time t is a sum of 2 vectors. Okay, so you always start with that initial vector r0, and then you add the displacement after a certain amount of time. So after, say, 5 seconds, the displacement will be the initial velocity, because the velocity is constant, just the initial velocity, so and so many meters per second, times 5 seconds will be so and so many meters in the direction of the initial velocity. Okay, and that's the displacement after 5 seconds. So that corresponds to that vector, and that corresponds to that vector. And we add them tip to tail. Okay, so graphical. So tip to tail. So again, I'm assuming that everyone is familiar with the basics of vectors, how to add vectors tip to tail, and so on. I just wanted to sort of illustrate that you can look at a simple kinematical equation like this with no acceleration, just constant velocity, purely in terms of vectors without splitting those vectors into x and y components, without choosing a coordinate system, x and y coordinate system, anything like that. So I think it's a really useful skill to help deepen your understanding of vectors as geometrical objects in and of themselves. They don't need to have a coordinate system or x, y components, all that kind of stuff. And this is really important because when you study other stuff, like later on, you study general relativity, or even just like vector calculus and in general relativity, these vectors are geometrical objects in and of themselves. Okay, you don't need coordinate systems. Okay, so, and I think it might help you to understand vectors a bit more deeply. Another way to think about sort of trying to figure out, let's say, what is the position of that baseball after 5 seconds has elapsed, given this initial position and that initial velocity. We do it graphically, or we can do it algebraically. Okay, and so I'm hoping that we can, that you guys can do it both graphically and algebraically. Okay, so how would we do this? Well, we would say the position vector at t equals 5 seconds. Well, what's that going to be? Well, we just look at this. It's the initial position vector r0 plus the initial velocity vector times the scalar 5 seconds. So you can multiply a vector by a scalar. Okay, and basically you just rescale the vector. It's a vector in the same direction, but it's just been rescaled. After 1 second it's this vector, after 2 seconds it's this vector, after 3 seconds it's this vector, after 5 seconds it's that vector. Okay, you're just rescaling a vector by scalar multiplication. Okay, and so then let's work this out. So r0, so in the last whiteboard, we had just made up an r0. We said it's -3 in the I hat, +4 in the j hat, if I remember. Yeah, so r0 is -3 in the I hat, +4 in the j hat. Okay, and the dimensions are length, the units are meters. Okay, and then we add to that the vector v0, which we took to be +4 in the I hat, +3 in the j hat, meters per second. That's the vector v0, the initial velocity vector, times 5 seconds. Okay, and so you'll notice that the seconds and the seconds cancel out. This vector has the units of meters, and this vector has the units of meters. You're adding 2 meters. In this case, this vector represents this vector, and this vector represents this vector. Okay, we're just adding them up algebraically instead of graphically tip to tail. And so let's see, so let's crank this out. So this is going to be -3 I hat +4 j hat meters, and then we just take the 5 inside. This is a dimensionless number, and we go 4 times 5 is 20. I hat +5 times 3 is 15 in the j hat direction, and the units that are left are meters. Okay, so we're adding a displacement plus another displacement. This is the initial displacement from the origin. That's r0, plus the displacement, given that it had an initial velocity v0, and that velocity was maintained for 5 seconds, and that's the displacement. Okay, and so then we add these guys up, and so we get negative. So when you add vectors, you always add like components, I hat plus I hat. You add the I hat components from both, so that's -3 plus 20 is 17 in the I hat direction, and then 4 plus 15 is 19 in the j hat direction, and the units are meters. Okay, and then so this is the I hat j hat, or the x and y components of this position vector at time 5 seconds. Has an x component, has a y component of 17 and 19. Okay, and so then you should also be able to figure out, well, what is the length? What is the magnitude of that position vector? How far away is it from the origin? And at what angle? This is the x-axis. Remember, all angles are measured counterclockwise from the positive x-axis. Okay, so we might be interested in that angle, and what do we call that? Phi. We call that phi at 5 seconds. Okay. And so we can work this out to figure out the magnitude. You just use Pythagoras. You say 17 squared plus 19 squared, square root is going to be 25.5. Okay, so after 5 seconds, our baseball is located 25.5 meters from the origin, and in which direction? So we can work out that angle, and so that angle is just going to be the arctangent of the slope, the rise over the run. Okay, so the rise is 19 divided by 17 is a number a little bit bigger than 1. Arctan of 1 is 45. Arctan of a number a little bit bigger than 1 should be a little bit bigger than 45, and it turns out to be 48 degrees. So at 48 degrees, okay, up like that. Okay, so that's great. Super. So this is the simplest possible situation we can think of is just moving when there's no forces acting, there's no acceleration, so the velocity remains constant. The kinematical result is like this, and position changes linearly with time, okay, as opposed to quadratically with time. Okay? So now we're going to make it a little bit more interesting. Now we're going to add gravity. So we're going to turn on gravity, and we're going to look again at this entire situation and see how things change. Okay, and I hope this is going to be sort of an illuminating way to sort of see this really simple trajectory type problem. So as soon as we turn on gravity, well, now there's a force. Okay, so the force is now different from zero, and so that means there's going to be an acceleration, which is different from zero. As soon as there's an acceleration, acceleration means that the velocity is changing, because the acceleration is the time derivative of the velocity. It's the rate of change of the velocity. If there's a non-zero acceleration, it means that the velocity is changing with time. Okay, so that tells you that, unlike in this case where the velocity is constant, we have the velocity will be a function of time, which is not constant. Its initial value, of course, will be v0, but that velocity is going to change because obviously this guy's going to now bend over on a parabolic trajectory. The velocity is initially in this direction, then this direction, then this direction, then this direction. So not only is the direction of the velocity changing, also the magnitude of the velocity is changing, and so on. So the velocity vector, magnitude and direction, will be changing. Okay? And so what is the acceleration in this case? So just thinking kinematically, so the acceleration is the force divided by the mass. The force is, mg. And so in vector notation, this would be an acceleration whose magnitude is g. So in this course, g is always a positive number. So g is positive 9.81 meters per second squared. So that's the free fall acceleration under gravity near the surface of the Earth. And g is always a positive number. It's never a negative number. Okay, so how do we, because positive and negative have to do with directions. This is the magnitude of the acceleration. In which direction is the acceleration? Well, we chose the I hat direction or x direction to be this way, to the, to the right, and the j hat direction or y direction to be up. Okay, and so we know that the acceleration is down, and so it's in the negative j hat direction. So it's negative j hat. But I want to point out, you might have chosen a coordinate system, x this way and y this way, y down, which you often do when you have like an object, say, falling off of a cliff. Well, the direction of motion is like basically down, so you might as well put the y-axis down. In that case, your j hat unit vector is down, and in which case you would write that the acceleration is of magnitude g, its direction is positive j hat. Okay, so the sign plus or minus here is associated with the direction, but g is always that positive number, 9.81. Okay, great. And so then in this case, when there's no force, no acceleration, this is the kinematical formula you have, very simple. But when there's an acceleration and the velocity is changing, the acceleration is constant in this case, this constant acceleration, and you all know the kinematical formula for constant acceleration. So in vector form, it would read this: the position of the baseball as a function of time as it moves on its parabolic trajectory will equal the same first two terms, r0 plus v0t. That's what would happen if there was if there was no acceleration, and then but there's an acceleration term which is plus 1/2 a t squared. There's a quadratic term. Now you might recognize this in x and y components. This is, say, x final equals x initial plus vx initial t plus 1/2 acceleration in the x direction t squared. And similarly for the y component. If you add those two equations with I hat and j hat components, you get this vector equation. And you can then think about kinematics, not in terms of components, but just in terms of vectors themselves as geometrical objects. This is really the sort of like the proper way to state kinematics using proper vector notation. Okay, so great. So let's look at what this equation says, because it's kind of cool. So let's see, do I have room to do this? So let's put the origin, say, down here. Okay, so we're basically taking this diagram and putting it over here. So this is our origin. And we say, okay, great. So when t is equal to 0 in this equation, v0 times 0 is 0, 1/2 a t squared when t is 0. These two drop out. And the position of the baseball at time t equals 0 is just r0. So relative to the coordinate origin, we displace ourselves by the initial position vector. Okay, so at t equals 0, this is the position of the baseball. And then remember, let's ignore this term for a minute and just sort of reproduce this part of the diagram. Okay, this part of the equation, just these two guys. Okay, so then when after 1 second has elapsed, then the object has undergone a displacement equal to v0 times 1 second. So 5 meters per second times 1 second is 5 meters. So it's moved 5 meters in the direction of v0. Okay, so that might look something like this. So yeah, something like that. So this is, that little vector is v0 times 1 second, the displacement of the baseball in 1 second had it been moving just with constant velocity. Okay, and if we keep gravity off for a minute, after 2 seconds, it would have displaced from the original position 2 times this. Okay, it just keeps moving with constant velocity along a straight line. All of these vectors have the same length. It's the displacement that an object would undergo in 1 second, moving with a velocity v0. Okay, constant velocity. But now something interesting happens. Now we have to add to each one of these points here. We need to add this term. So what is this term? So this term, say for instance, after 1 second, say what is this term at 1 second? So you go 1/2 acceleration times 1 second squared. Okay, so that's 1/2. The acceleration is negative g j hat, and then 1 second squared. Okay, and so what does that turn out to be? So that's going to be, just numerically, this is going to be 9.81 times 1 times 1/2 is 4.9. Okay, there's a negative sign there, it's negative j hat. And so what this does is, these are all displacements. This is the initial displacement. This is the displacement had the object been moving with constant velocity after a certain amount of time. And this is an additional displacement that takes place because gravity is acting and the baseball is actually in free fall. It's always accelerating down. It's always moving faster and faster down. Okay, and so what this says is that the additional displacement due to the action of free fall, okay, takes the baseball from this point and it drops it down a little bit. Okay, so let's assume that this little vector over here, because they're going to get bigger. Okay, so we'll start with a really little one. So this little vector is negative 4.9 j hat. That's how far an object falls in 1 second. Okay, is 4.9 meters. Oh, sorry, the units here are meters, because this is meters per second squared times seconds is meters. Okay, so it falls, has a displacement of 4.9 meters in the negative j hat direction. And so to get to the position of the particle after 1 second, we start at the initial position, we add how much it was displaced under the action of constant velocity, but then we recognize, oh, wait a minute, it wasn't constant velocity. Velocity is changing because there's acceleration. That provides a correction. This is a free fall correction, which is that little guy. So you add that vector, plus that vector, plus that vector, tip to tail, and you end up at that position. Okay? And then you say, okay, well, what happens at 2 seconds? At t equals 2 seconds, the position is r0, this guy, plus v0 times 2 seconds. So the object, if there's no gravity, its displacement after 2 seconds would be this plus this. It'll be sitting here. Okay, but during that whole 2 seconds, it has been free falling. Okay, so how far does something free fall in 2 seconds? Well, you just do this same calculation, but replace 1 second with 2 seconds. And so it's not just 2 seconds, it's 2 seconds squared. So the 1 becomes a 4. And so you take this number and multiply by 4. Okay, and so take that little vector and multiply by 4. Let's make it about that big. Okay, so remember, this one is 4 times bigger. Let's call this, if this is 1 times, this vector here, the free fall during 2 seconds is 4 times bigger than the free fall during 1 second. Okay, and then we look at 3 seconds. Well, instead of a 1 there, that'll be a 3. 3 squared is 9. So then we multiply by 9 instead of by 4. Okay, and so if this is 4, then let's say that this is about 9. Okay, so this is 9 times. And then on and on. Okay, so 4 squared is 16 times. And so if this is 9, 16 is maybe about, 16 is maybe about like that. And then next will be 25. Okay, next will be 36. So this vector is 36 times as long as this vector. This is how far it fell in free felled in 1, 2, 3, 4, 5, 6 seconds. Okay, and so on. So these increase, the lengths of these free falls under gravity increase quadratically with time. So length increases quadratically with, this is really squeaky, quadratically, that's the quadratically with time. Okay, so that's what makes you have a curved path. Okay, this is a free fall, this is a parabolic trajectory. What gives it the curvature is the t squared term here. Because this term alone, just a linear in t, well, that's just going to be a straight line. What makes it a curved path is this quadratic term due to the acceleration. And so this is a beautiful way just to understand the basic idea of one of the most basic sort of kinematical formulas, okay, graphically and in terms of vectors. So I know you understand this kind of problem in terms of xy components and so on, but I think it's really useful to re-envision that problem purely in terms of vectors, so you just get more familiar with what vectors mean. So then at any particular time t, let's say time t is over here, you have this position vector. So r, yeah, let's just call this r at time t. Okay, what I want to do is draw a slightly different diagram. So at the end of the day, what you are doing to figure out the position under constant acceleration like gravity is you are adding, graphically, tip to tail, 3 vectors. Okay, so what you do is you start at the origin. So I'll just sort of summarize this diagram. You start at the origin, okay, and then you say, well, sorry, this is the origin. You start at the initial position vector, so you take that vector, and then you add to that the displacement the object would have if there was no gravity. If you just threw the baseball and there was no gravity, it just went on a straight line with constant velocity for a certain number of seconds, it would have undergone some displacement, v0 times so and so many seconds, v0 times t. So this is r0. This here is v0 times t. Okay, but then we turn on gravity and we say, well, wait a minute. Actually, you have to also add to that now the free fall. Okay, and so the free fall is this term here. So this is 1/2 a times t squared. And so this is a sum of 3 vectors. You add them tip to tail like this, and then that gives you the position of the baseball at time t. So, and if you want it in between times, it would look like that. Okay, so anyways, I think that's a really sort of nice way to think about basic kinematical formulas like this. You already know them in XYZ component form. Think about them in terms of purely vectors. It'll help you understand vectors a little bit better. And remember, you really got to understand vectors well. Really try to master vectors in this course before you get to second year, okay? Okay, awesome. So let me erase the board, and I'll come back with some more stuff to do with forces and so on.